So last couple of things we're going to do on inequalities. First of all, the Cauchy-Schwarz inequality. So this theorem 22 says the Cauchy-Schwarz inequality states that, so we have two sequences of numbers here, a1 to an and b1 to bn. They're all real numbers. Right, and this is any real numbers. It could be positive, negative, or whatever. Basically what it says is, so a1 to an as a sequence, b1 to bn as another sequence of real numbers. The two sequences have the same number of numbers, n numbers. This inequality here is called the Cauchy-Schwarz inequality. Basically, if you take the first sequence and you square all the terms and add them, take the second sequence, square all the terms and add them, and then you multiply those two, that is always going to be greater than or equal to, if you take the pairwise products, a1, b1, a2, b2, a3, b3, etc., up to an, bn, and then you square that. Right, so basically what this means is you could write it in summation notation like this. What you have is the product of the sums of the squares is greater than or equal to the square of the sum of the products. Right, product of the sums of the squares is greater than or equal to the square of the sum of the products. There are a couple different ways you could prove this. You could do it using take up it as a quadratic and consider it discriminant. I wouldn't bother to try to prove it. It is true, it is something you can use. Note that you have equality here if and only if the sequences are proportional, meaning that the ratio of a1 to b1 is the same as the ratio of a2 to b2 and so on. They don't have to be the same sequences, but it must be the same ratio. For example, if a1 is twice b1, a2 is twice b2 and so on, then this would be equal. Let me show you an example of that before we look at the other form. So example 24, if you wanted to prove that 3 times a squared plus b squared plus c squared is greater than or equal to a plus b plus c all squared. Notice I have a squared plus b squared plus c squared. I could take that as this, where is it? This here directly, and then I have something squared. Anytime you see things like this, where you have on one side sum of squares and then the other side square of the sums or products or something, then think of Cauchy-Schwarz. Right? So if I let, sorry, if I let, so I have 3 terms in each, right? So it's sequences of 3 terms. So if I let a1, a2, and a3 be 1, right, I'm going to get 1 squared plus 1 squared plus 1 squared gives me 3. And then if I just let b1, b2, and b3 be a, b, and c respectively, I'll get this. And then on the right-hand side, remember, these are 1 and these are a, b, and c. So I'll get 1 times a plus 1 times b plus 1 times c all squared, which is this. So this follows directly from the Cauchy-Schwarz inequality. Right, so you could try to prove this. Otherwise, I'm not sure how easy it would be to do. Just one thing to note, anything you can prove using Cauchy-Schwarz, you can also prove using AMGM. It's just that the construction for it might be a little more complicated. So what you could do is try to prove this using AMGM as well if you want. Or maybe QMAM or something like that. A more useful form of the Cauchy-Schwarz is sometimes this, the Cauchy-Schwarz in angle form. So it's another way of writing this basically. So again, I have sequences a1 to an and b1 to bn. Now this time, instead of just a1 squared plus a2 squared plus etc., I have a1 squared divided by b1. Now just note, this is not b1 squared, right? It's just b1. Also, a1 to an are real numbers, but b1 to bn are positive real numbers. Right? You need the positive part because this is no longer squared, so it has to be positive to make sure that this entire thing is positive. So I have basically a1 squared over b1, a2 squared over b2 plus etc. times, and also this is no longer squared. Where is it? This is no longer squared. It's just b1 plus b2 plus etc. plus bn. This was greater than or equal to a1 plus a2 plus a3 etc. plus an squared. All right. I guess another way you could think of this is if you divide it, remember b1 to bn are all positive. So if you divide it by this, product here, the other is sum here, then it might look something kind of symmetric. So what you would have on this side, you would have a1 squared plus over b1, the sum of those things. And on this side, you sum the a's squared and then divide by the sum of the b's. Right? So what I mean is, if this summation, if you carry it on this side, you have the sum of ai squared over bi is greater than or equal to the sum of ai squared over the sum of bi. All right, remember the squares on the outside. These are not, well, it's good if you know them, but like I said, if you could do it using these, then you could probably do it using AMGM. So the AMGM and all those related inequalities are much more useful to know. You need to know those, right? I'll put it that way. These you don't necessarily need to know. It's only more complicated problems when you use these. And a simple example with the Cauchy-Schwarz and Engel form, if you want to prove this, right? It doesn't look like it might be easy to prove in general, but if you use the Cauchy-Schwarz inequality, so you let A1 be A2 be 1, A1 and A2 be 1, A3 is 2, A4 is 4, and then B1 is, well, these just go A, B, C, D. Right? So using 1, 1, 2, 4 and A, B, C, D. So basically what you're going to have is 1 over 2 plus 1 over, sorry, 1 over A plus 1 over B plus 2 over C plus 4 over D. All right, is that correct? What am I doing? Oh, it's squared. You're squaring them. So 1 over A plus 1 over B plus 2 squared is 4 over C plus 4 squared is 16 over D. All right, that's how you get this. And then, well, these terms here would just be A plus B plus C plus D. And this would be 1 plus 1 plus 2 plus 4 all squared. Right? So 4 and 2 is 6 and 2 is 8 squared, that's 64. And then when you divide by the other term, you get the right hand side. So again, this follows straight from the Cauchy-Schwarz inequality in Engel form. And then I mentioned this before, the rearrangement inequality. So this is the general form of it. If A1 is less than or equal to A2, and then B1, etc. No, this doesn't just have to be less than or equal to, right? The signs could be the opposite, but it must be the same signs for both. So if this was A1 greater than or equal to A2, etc., it would still hold if this was also greater than or equal to. Right, and the maximum, basically what it says, the rearrangement inequality says, the maximum sum you could get with pairwise products is if you line them up. If you take A1 times B1, A2 times B2, etc., to AN times BN and multiply those and then add them. That is greater than any other pairwise sum you take. Permutations of pairwise sums. So an example for the case with 3 and 3. So if you take AX plus BY plus CC, C times Z, that's greater than or equal to if you take AX plus BZ plus CY, or if you take AY plus BX plus CZ, or any of the other 3 combinations. The maximum would always be AX plus BY plus CZ. Now, one thing to note here is if you're looking at a single sequence twice, right? If you take X is less than or equal to Y less than or equal to Z and the same thing as the second one, you actually get this, right? Because you take X times X, Y times Y, Z times Z is less than, is greater than or equal to any other combination. So XY plus YZ plus ZX. So this is, this follows directly from the rearrangement inequality. You could also prove this using either AMGM or just factorizing and grouping as perfect squares. Right, these exercise questions are a little complicated, so you could try them, but you may have some difficulty with them. The first two may be doable, but the others might be a little difficult. Any questions on those before we move on? Either Cauchy-Schwarz or rearrangement. Like I said, they are more advanced techniques. So for right now, it's not necessary that you know them. The one that you do need to know is AMGM, at least AMGM. If you know the others in the chain, if you know QM and HM as well, that's fine. That's good to know. But AMGM is mandatory. Okay, so next, the next couple things like absolute value and floor and ceiling functions, I'm just going to briefly go through. The absolute value of x is basically the magnitude of x. So if x was greater than or equal to 0, it's already great. It's non-negative, so it would just be the value of x. Now, if x was less than 0, you want the magnitude. If x is less than 0, it's a negative. So to get the magnitude, you multiply by -1 to make it positive. Right? So that's how it's defined. All right, some examples and then some properties. This is always greater than or equal to 0. All right, and well, these are the properties here. I'm not going to go through those. You all can look at them. So if you had something like, say this, to solve an equation involving a modulus or absolute value, then you would have to take cases, basically. So you're looking at, based on the definition of the modulus, right? We know the modulus of x minus 3 is either x minus 3 or the negative of that, depending on the value of x. Basically, when this thing is non-negative, meaning when x is greater than or equal to 3, it would just be the value you have. When x is less than 3, then you have to take the negative of that to make it positive. Same thing down here. This thing is 0 when x is minus a half. So minus a half will be the boundary point. Similarly, 3 would have been the boundary point here. So when x is greater than or equal to minus a half, this thing is going to be, well, this is going to be just the value it had. But when x is less than minus a half, it becomes negative, so you have to multiply by -1. So using that, you know, the points x is equal to 3 and x is equal to minus a half are the what we call critical points. Those are the points where things change. So you need to you would have to consider different intervals using those points. So first you have x is less than minus a half because that's the smallest one of the two. And then you go minus a half to 3 with minus a half included because it's included here, but less than 3, so not included. And then lastly, x is greater than or equal to 3. Right. Another way you could do it is just keep these as strict signs and then consider what happens at the points separately. So that would be 2 other cases to consider. But based on these, the question itself here, you can do it like this. So suppose that you're looking at this interval, x is less than minus a half. Now if x is less than minus a half, then the modulus of 2x plus 1 is going to be given by this. X is minus a half lies in this interval as well. So the modulus of x minus 3 is going to be given by this. So we could, in this equation, I could replace modulus of x minus 3 by this and modulus of 2x plus 1 by this. Right? They're both negative, so we have those definitions, and therefore the equation becomes this. You solve that and you get x is minus 2. Now, when you do this, it's important. When you get the value of x, make sure it's in the interval, because sometimes it's possible that it doesn't have a solution. So it gives you a value of x that is outside the interval. In this case, minus 2 is in the interval you want. X is less than minus a half, so that's fine. All right, next one is this interval here. So again, now in this interval, now we're looking at x is greater than or equal to minus a half, right? So modulus of 2x plus 1 is just 2x plus 1. But it's less than 3, so this thing is still the negative of x minus 3. So again, we substitute and we solve and we get x is 0, which is okay because x is 0 lies in this interval. All right, last interval to check is x is greater than or equal to 3. So they're both positive, so we could just drop the modular signs and work it out. Now, when we solve this on this side, this time we get x is minus 6, which is a problem, right? Because x is greater than or equal to 3. Minus 6 is not greater than or equal to 3. So this is a contradiction. It means that in this case, there's no solution. So the only answers are x is equal to minus 2 and x is equal to 0. All right, so this question, you do something similar. Now, this is a proof. So again, you consider the critical points of this, which would be 0 and 1. So basically, you check the intervals x less than 0, from 0 to less than 1, and then from 1 onwards. And you see that in both of those, all three of those cases, this is true. All right, this one, I want to see what you all do for this. And this one as well. Right, floor and ceiling functions. This is more just defining what they are. We've been using them already, especially floor function. We've used it in number theory. We've also used it in combinatorics, so you would have seen it already. Floor function is basically the greatest integer function. It's also called greatest integer function. It's the greatest integer less than or equal to the value you have. Be careful with the negative numbers because remember it's less than or equal to, so if you had a negative 2 point something, the actual answer would be -3 when you take the floor because you go down, not up. Right, now using the floor function, you can define the decimal part or the fractional part of a real number. So that's curly bracket x. That basically means it's the fractional part between 0 and 1, or from 0 to less than 1. It's defined as the value of x minus the greatest integer less than or equal to x, or the floor of x. So some examples here. With negative numbers, there are actually two ways you could define it. You could actually, if you wanted to, you could define it as the fraction, which is 0.3, but I'm using the definition, the same definition throughout. So based on this definition, it's actually going to be 0.7 because the greatest integer less than or equal to this is -3. Right, and there's some properties here for floor and fractional part. Now, there are some questions where you actually have to introduce things like the fractional part and the floor function to help you. Or maybe it already has the floor function in it and you would actually have to introduce fractional part to help you. I think there's some questions like that, maybe in the miscellaneous exercise. Right, and then ceiling function is just the opposite. It's the smallest integer that is bigger than or equal to x. Right, these I'm not going to talk about too much because it's really just to introduce the idea of it. All right, so here we have a basic, a fundamental, I guess, introduction to what are sequences. Now this is sequences, but we can also talk about series at the same time as we go on. A sequence is basically a list of terms, right? So it starts A1, A2. You could also start at A0 if you want, depending on how you define a sequence. So basically you list them A1, A2, A3, and it could be finite, meaning it could stop at some term AN, or it could be infinite, it could go on forever, right? That is what a sequence is. Now, I don't know if it's defined later on. I don't think it is. But a series, right? A series is just the sum of the terms of a sequence. So if I had a sequence A1 to AN, the series corresponding to that would be the sum of those. So A1 plus A2 plus A3, etc. to AN. So when we talk about things like APs and GPs, we'll talk about the series for that as well, the summation of it. There's some basic examples of sequences. So you could have a finite sequence from 1 to 5, or an infinite sequence of positive integers that go on forever. You could have a sequence consisting of the days of the week, or an infinite sequence of constant numbers. That is also a sequence. Okay, and two of the most famous sequences that you probably know of, an arithmetic progression or an arithmetic sequence. Right, it's just a sequence where the consecutive terms have a common difference. So if the first term is A, then the second term is A plus D, and you keep adding D. Right, and if it terminates at an nth term, the last term, because you start with A, so it's A plus 0D, the last term will be A plus n minus 1D if you want n terms. Right, if you started with 1, you would stop at n, but if you start with 0, then you stop at n minus 1. Right, and then the sum of the terms of the sequence, so this is really what a series is, right? The series is the sum of the terms that is given by this formula. And if you want to prove this, you could list the terms like this and then list them in reverse order. So you would have A plus n minus 1D here, A plus n minus 2D, all the way down to A. And then when you add them, you'll see that you get the same sum each time. And this is the sum you'll get each time. You get 2A plus n minus 1D. Right, and since you've added the same sequence twice, you have to divide by 2. And also this term appears n times because they're n terms, so you have to divide by n as well. So you have to multiply by n to get the actual sum. You divide by 2 because you counted it twice. Right? If it's an infinite sequence or infinite AP, it doesn't have a sum, it just goes to infinity. The only infinite AP that has a finite sum is a sequence of zeros. Even if it's a sequence of constants other than zeros, that sum would still go on forever. All right, corollary, the sum of the first n positive integers is given by this. So if we're talking about the first n positive integers, it means that a is 1 and d is 1. So substitute a is 1 and d is 1 into here, and this thing simplifies to n plus 1. Right, and the second one is a geometric progression or geometric series. So if the first term is a, the second term will be a times some ratio, and then you keep multiplying by r each time. Right, so if the GP terminates at an nth term, then that nth term, because you multiply by 0, r to the power 0 here, the nth term will have r to the power n minus 1. So similar to before, if you start with r to the 0, you stop at r to the n minus 1. Right, and the sum is given by this. Right, so if you want to see why this is true, consider the factorization of r to the n minus 1. R to the n minus 1 is r minus 1 times basically the sum of these things, right? So if you divide by r minus 1, when you multiply by a, you'll get those. Right, if it's an infinite series, if it's an infinite sequence and you sum that, right? If the modulus of r is less than 1, then as n goes to infinity, this will go to 0. Right? So if this goes to 0, you'll get minus 1 over r minus 1, which is just 1 over 1 minus r. So this would simplify to this. But if the magnitude of r is greater than or equal to 1, then this would just blow up. Right? So it doesn't actually have a finite sum in that case. Right? Because if r is equal to 1, you have division by 0. That's a problem. Right, so most sequences you can get a closed form expression fit. So arithmetic progressions can be written in this form. An is a plus n minus 1d, that's the nth term basically. And geometric progressions, the nth term is this. So that's called a closed form formula fit, or closed form expression. Right, now sometimes you might have to find closed form expressions for sequences given what is called a recurrence relation. So a recurrence relation is something like this down here, where basically the n plus 1th term is defined based on the nth term, or maybe n minus 1th term, or something like that. Essentially what you have is some term is defined on some of the terms that come before it. That is called a recurrence relation. You use the smaller terms to get the bigger terms and so on. Right, now in this example, it starts with 0, it doesn't start with 1. So a0 is 1, and then you could substitute n is 0 in here to get a1 would be a0 plus 1. So a1 would be 2. And then similarly, you could get a2, a3, a1, etc. So if you want to find a closed form expression, there are two ways you could do it. One way is to write it using the definition of an AP. So if you look at this recurrence relation, you carry the an term on the left-hand side, you'll get this. This means that the difference between two consecutive terms is 1, which is the definition of an arithmetic progression, right? Because it means that for any two consecutive terms, you take the difference and it's constant. So what this means is that the constant is 1. And also the first term here is defined as 1. So it's a AP with first term 1 and common difference 1. Right? No, but it's slightly different from how it's defined above, because above, where is it? Well, based on this thing here, n would have been starting at 1 for these, right? But now I have n starting with 0. So it's a slightly different formula you're going to use, right? Basically, since the first term is 1 and the common difference is 1, right? When you substitute here, you'll get 1 plus n minus 1. But it's not exactly the same because, like I said, here n starts with 1, here you want n to start with 0. So when you actually work it out properly, the sequence becomes this, right? And you could test it when n is 0, you get A0 is 1, which is defined here. When n is 1, you'll get A1 is 2, which we calculated, and so on. So this is correct. Another way you could do it is using induction. So if you didn't work it through like this, but you guessed that this is one nice thing about sequences. If you could guess what the actual formula is, then you can use the recurrence relation to prove it by induction. So if I had guessed that an was this, then I can use induction to prove it. So base case is trivial because it's defined. So assume that ak is equal to k plus 1, and let's try to figure out what ak plus 1 is. Right? Now, from the recurrence relation, ak plus 1 is this plus 1, which is k plus 1 plus 1. Right? But that's exactly what we wanted to prove, so you're done. All right, that's it. Okay, so the last two things we have to talk about here are polynomials and functional equations. This is going to take a little bit of time, so I don't want to kind of cut it in between. So we'll take a break here and start back, let's say at 4:35. All right, so is that okay with you all? Does anybody have any questions before we take a break?
Or like recurrent relations with the an term. Well, the an plus 1 term being dependent on the an term, but it has like powers to the an and stuff. How we could go about finding a closed form for that?
It depends on the question. Like this is a simple example, but for more complicated questions, you'll have to manipulate it in different ways. Honestly, with sequences, what I usually try to do is try to find as many of these smaller terms as possible and see if you could see what the formula is. Try to kind of figure it, try to like list as many terms as you could and try to see if you could find a pattern, basically. There are some standard methods you could use for certain sequences. We wouldn't go into those right now because I don't know how helpful they'll be. But I'll see later on, I'll see if I could send you some software to go through.
Okay, cool.
What you just asked, is there a particular question you had in mind there?
Two questions. I think it was number 1 from the Canadian Junior Math Olympiad.
Yeah.
I was trying to find a closed form for it, but the closed form I found had a set of nested roots of root 5 minus 1 or something.
Okay.
And the other one is, I think, number 3 in the other Math Olympiad that you sent. I think I got it out, but I didn't find a closed form for it.
This one?
Yeah.
Prove the sequence contains no powers. So something like this might be difficult to figure out for a closed form when you have this squared plus that. Let me look at the other one. This is kind of similar to the other one. Just see in terms of well, they switched up.
I know generating functions is a pretty good one, but I don't know if it could work if you have a squared term.
Yeah, not sure. Okay, so let's see. an plus 1 squared plus an plus 1 is an. And an squared plus an would be an minus 1. If you subtract those, all right, let me stop recording this thing first of all.
For that one, I also try to find a closed form, but like the